Hello, this is Mr. Springer, and I'm making a short, hopefully short video on electron configurations. I know some of you struggle with this, and so let's see if we can talk it through one more time, and maybe it'll make more sense to you. Basically, electrons make up the majority of chemistry in high school, almost. There's very little that we do that involves anything other than electrons. Early on in the year, late in the year, but most of the year, it's just electrons. Valence electrons are involved in chemical reactions and bonding, but not all electrons are valence electrons. And the current science is that electrons occupy different energy levels and orbitals of different shapes, and they are some crazy shapes. You can Google those if you want. I would not, but you might want to. It can be known where to find electrons, so we might as well know where they are, right? So, moving right along. Energy levels, that's the first step we want to look at, and those are sometimes called shells. I like to think in terms of layers of an onion. The energy levels are numbered 1 through 7, and those are the same as the horizontal rows of elements on the periodic table. They're often numbered on the left side of the periodic table. At least ours are there. Now, it does get a little bit overlappy and confusing at times, but just stick with the program and you'll be fine. Level 1 is the level closest to the nucleus. It's the smallest. It's only got one sublevel, and that's called S. Level 2, just like instead of level 1, it's got two sublevels, S and P. Level 3, as you might imagine, has three sublevels. They're S, P, and D. Level 4 has four sublevels, S, P, D, and F. So far, so good. Levels 5, 6, and 7 continue the trend, although 5 only goes through F, 6 only goes to D, and 7 only goes to P. They will go farther if they ever invent or create more, and create's not a good word, if they ever synthesize elements beyond what we now have. I'm not sure of the point, other than to get a Nobel Prize or to get your name on the periodic table or something like that, but it is possible that we may end up with something bigger than a fifth level, whatever the fifth sublevel of level 5. I'm thinking it's going to be G, but I don't know. Or with 6 or with 7. So, well, maybe you'll see that in your lifetime. I don't expect to see it in mine. S sublevels, one orbital. Orbital is where you're going to find electrons. It's a solution to a mathematical equation. An orbital has a maximum of 2 electrons with opposite spins. So S has 1 orbital, P is 3, D is 5, F is 6. 6? That's not right. 7. Just remember 1, 3, 5, 7, and you got it. 1, 3, 5, 7. 1, 3, 5, 7. It's like 2, 4, 6, 8, only less. 1, 3, 5, 7. Levels, so we got these 4: level, sublevel, orbital, and spin, and those are called quantum numbers. And if you take a higher level class than what you're in right now, or maybe you're in that higher level class, so if you're in a class higher than, what do you mean? Other people watch this other than Southwood students. I've got other viewers. Some people are in other classes. Leave me alone. 4 quantum numbers. If you're in a higher level class, you might see those. But if you're in first year regular high school chemistry, or maybe a introductory college chemistry course, you may not need to talk about those much. But anyway, no 2 electrons in an atom can have the same set of 4 quantum numbers. So everything has its own unique address, if you will, within the atom. And it's those 4: level, sublevel, orbital, and spin. Those all have to be different for every electron in an atom, but you don't care. All right, rules. They're always good to have rules. So always put the electron in the lowest energy orbital possible. Don't pair up until each orbital in the sublevel has at least 1 electron. And make sure the spins are represented, both electrons are opposite spins in an orbital. We use up and down arrows to represent spin and whatever. So let's write some electron configurations. I've got 4 written here: carbon, magnesium, titanium, and tellurium. You might have a document looks something like this. If not, they're easy to make. Okay, so we want carbon and carbon. Carbon has 6 electrons. Well, it's got 6 protons, so I assume it has 6 electrons, right? And I'm going to start here with 1s. There's 1. There's 2. We have finished 1s. We can now go on to 2s. Remember, we start at the lowest level possible. If there's a spot, we put it in there. 2s. Now we've used 4 of the 6. 6 minus 4 would be 2. We have 2 left. We can't pair them up. We can't do this. No, you can't. You cannot do that. That violates this rule over here about make sure don't pair up until each orbital in the sublevel has 1 electron. So we can't do that. So what can we do then? Let's do this. 2, 4, 6. We got 6 electrons there. Everybody's happy, happy, happy. All right. Oh, that's probably a violation of copyright. Never mind. I did not say that. Next is magnesium with 12. Electrons. Let's start putting them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Should we go here? No, but it's still 3. That doesn't matter. We got to fill this 3s before we can go into 3p. 2, 4, 6, 8, 10, 12 electrons. We are good. All right, the third one. Titanium with 22. You got to get to 22. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. See how we did that there? Did you notice that 3D is higher energy than 4s? But it's 3. I know, but it's still higher. When it's filling, it's higher. Once it's filled, I'm not sure what it does. It may get a little less. It has to do with the way, how the penetrating ability of the electrons into the, I don't know. There's a lot of stuff there. Look that up in your book. I'm telling you how, not why. Okay. So there was your titanium, and the fourth one is tellurium at 52. I wanted that to be this color. 52, that's a lot. What happened? If I'm not mistaken, that's 18, 20, 30, 36, 38, 48. How far are we going? 52. 49, 50, 51, 52. That just about filled all my spaces. Okay, so that's the arrow diagrams way. Let me clean that up a little bit. That's how we do it with the arrows. The next thing that you might be asked to do, I know my students will be asked to do this, is sometimes we need to identify the valence electrons. Remember, the valence electrons are the ones that are involved with bonding, and the valence electrons are the electrons in the highest occupied energy level. Let me say that again. Valence electrons are in the highest occupied energy level. So on the carbon, I've got 1s, I've got 2s, and 2p. Clearly, the second energy level is the highest occupied. It's all the ones in the highest occupied energy level. So it's those right there, and there are 4 of them. And if you've got a video on valence electrons, you know that the valence electrons is the same as the A group number on the periodic table, and carbon is in column 4A, group 4A. He's got 4 valence electrons. We did it right. Okay, magnesium. We've got 1, 2, and 3 energy levels. See, there's 2, and 3 has electrons in it. There's not any in 3p, though. But this would be your valence electrons, so it's really just these two, right? Those two. So it's got 2. And it's in group 2A. Huh. See how that works? Titanium, we've got 1, 2, 3, and 4. Of those, the highest is 4. 4 is higher than 3. These 3 ones are not valence. They're not valence electrons. The 3Ds are not, because it's only in the highest level. The highest occupied level is 4. So it's the 4s and the 4p. There just doesn't happen to be any in the 4p. So there are 2 valence electrons. Well, this isn't in group 2A. No, it's in something B. 4B. And B doesn't play. We can't tell valence electrons from that, from the B groups. So we just have to count them, and that's 2. Most of the time, if you're introductory level, if it's a transition metal, call it 2. At least half the time you'll be right. Probably more. All right, and finally we got the TE52. It's got electrons in the 5th energy level. Remember, 4 is less than 5. So those ones there are not valence electrons. The valence electrons are the 5s and the 5p. We've got a total of 2, 4, 5, 6. 6. We're in group 6A. 6 is appropriate for 6A. We can use this type of configurations to look at whether something's got an octet, how many bonds it's likely to form, where it could form bonds, where it could gain or lose electrons. All that kind of stuff is kind of nice to know. However, a lot of times your teacher or professor won't want to see this. They might not even give you an opportunity to do this with the blanks. What they might want or prefer is that you do the more condensed. I forget, it's got a name, but I can't remember what it is right now. But anyway, we go 1S, and there's 2 arrows there. 1S2, 2S2, 2P2. And there is your electron configuration. That's the actual electron configuration. I call this the arrow diagram. This is the electron configuration. That's what I call it. You could, from here, easily identify your valence electrons. It's those 4. Seems reasonable. Okay. On this next one, the magnesium, I've got 1S2, 2S2, 2P6, 3S2. Valence electrons, 3S2. On the titanium, well, I'm going to need some space. Make some space right here. We're going to go 1S2, 2S2, 2P6. All right, see where we're at there? 1S2, 2S2, 2P6. 3S2, 3P6. 4S2, 3D2. There's your electron configuration. If we want to know valence electrons, we can just circle these right here. It's the 4s, not the 3Ds. It's just the 4S, because there is no 4P yet. And this last one here, this tellurium. Wow, look at that. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p4. And my valence electrons are right here. There were 6. That's a lot of writing. That's an awful lot of writing. I'm going to clear some of this off. Do I need to clear this off? Let's not clear this off. Let's go down here. And let's do, let's say, argon. Argon is number 18. Argon's number 18. It's got 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18. And 6 of those are valence electrons. It's those 6 right there. And it's these 8 right here. Since argon has 8, a full set of 8 valence electrons, it has an octet, which is what all the elements would like to have if they could like things. That's what they would like. They really don't like things, but that's what their chemistry makes them try to have an octet. So, with that being the case, oops. Oh, where was I going with that? You can see here in the titanium example that right here, is same as the electron configuration for argon. Okay, where is that here? There's argon. Since argon is a noble gas end of the row, we can substitute in argon for all of this right here. We'll just substitute in an argon. Let me erase all this. And here's how we'll do it. We'll say argon for S2, 3D2. That's called the shortcut method, maybe, or the noble gas configuration, or something like that. It can be done. It's not terribly difficult. It can be done. You don't have to do it in my class. Maybe where you are, you do, but you don't never have to for me. Not in first year. Let's redraw this. All right, so here is all of that. Let's clean this one up too. Let's see, we had 4p6, 5s2, 4d10, 5p2, 4. We need to find the previous noble gas. The noble gas is the end with p6. So here is 4p6. 4p6 is krypton. So we could say krypton. 5s2, 4d10, 5p4. You can still see the valence electrons. It saved you quite a bit of writing. For my students, if you need to do this, do that. If you need to do all of this, from this, that's fine too. If you want to do this, that's perfectly acceptable also, unless the directions say write the complete electron configuration. Okay? So hopefully this cleared things up for you a little bit. We'll find out. See you next time.